The stormtime behavior of low-energy charged particles in the vicinity of the plasmapause by Rita Sagalyn.
I'm going to discuss the low-energy measurements of the plasma obtained with two AFCRL electrostatic probes flown on the Engine 5 satellite. What I will do is stress those aspects of the results which bear on the energy exchange between the inner and outer magnetosphere at these times. Now, the conclusions are based primarily on the study in detail of 8 magnetic storms obtained during the first year of operation of Engine 5. So I will compare some of the results because they are relevant to slightly earlier data we obtained on OGO 3 with similar probes at much higher altitudes. Now, these two spherical probes were designed to measure the properties of charged particles, ions and electrons between 0 and 700 eV. They were operated in the following way. That is, during one orbit, one probe would be operated between 0 and 15 eV, sequentially getting the total density and the energy of a given charged particle throughout one orbit. In the next orbit, we would filter the thermal particles and then measure the total flux of particles between energy 15 to 700 eV, and then periodically throughout this orbit also measure the differential energy distribution of these particles. Now, so one can see that on any given orbit, we had the polarity such that we were always measuring the low energy particles of one sign and the higher energy particles of the other sign. Engine 5 was launched into a polar orbit of 81 degrees inclination with an apogee of about 2,500 kilometers and a perigee of about 500 kilometers. Now, I will, on each storm, we analyzed data from 60 to 100 orbits so that we could, with significant spatial resolution, we could obtain information about the longitudinal behavior, the local time behavior, as well as the variations which occurred in both the northern and southern hemispheres. I'm going to first discuss results on the night side because they are distinctly different from the results obtained on the day side on any storm. In the first slide, discuss the results of the storm of mainly the illustrations will be perhaps from the storm of October 29th through November 4th, 1968. I chose it because a number of the people here have studied various aspects of that storm, Roble, Hoke, Chappelle, and so forth. Now, in the first slide, I just want to show you the variation of KP with time. Oh. Yeah, on the lower portion, look only at the lowest portion of this curve, which shows the KP versus time on this curve, and in the lower part also portions at times when red arcs were observed throughout this storm. The maximum DST variation during the storm occurred about November 2, which was 100 gamma DST variation. Now, on the pre-storm values from October 20, we had something like 6 orbits of data on the night side on October 28th and 29th. And on these, we did see on the night side a distinct electron trough at 62 degrees invariant latitude and at L equal 5.5. Starting at about 12 UT on October 29th, when the first major DST changes occurred, we saw significant variations from this behavior. That is, in this first slide, we show on the top upper portion both electron density and electron temperature as a function of invariant latitudes, perhaps, or L in the lower portion. And one first can see that for both the soft particle fluxes, that is in the lower portion, particles with total energies, the total flux of particles with energies between 15 and 700 eV, that first of all, the boundary of the where's the stick? Oh. First of all, the boundary of the plasmapause, of the trough, the equatorial boundary, has moved from 62 degrees to something like 52 to 54 degrees. At the same time, and this is a general feature, the electron temperature, while it's something like 2,800 degrees, equatorward of the boundary increases very sharply up to something like 8,000 degrees, and it's quite irregular throughout the storm, but very high, going not only through the trough, but into the precipitation zones. And I think a very important point to note here is that the soft particle fluxes are also increasing at the same time. That is typically before the storm, the particle fluxes we're typically at a level of about 10 to the 7th per square centimeter per second, and increasing maybe only a factor of about 2, at most 1.5 to 2, going into this trough region. And in the storm, this is in all the storms we see once in any well-established storm, that the soft particle fluxes, hypothermal fluxes, do increase significantly, like an order of magnitude. Now it's important to note that these represent energy densities of about 10 to the 8th. Their average energies for protons are about 100 eV, and this represents an energy density in this region of these local hyperthermal fluxes of about 10 to the 8th per cubic centimeter. Now, in the next slide, a few days later, I show a similar one. We have some 100 of orbits, which I could show people with this kind of data. Again, we always see, I think we can see that, again, as you enter the trough, the electron temperatures increase significantly. There are very large variations, of course, but certainly well high enough to see, to produce, for example, SAR arcs. At the same time, the soft particle fluxes increase between, again, 10 to the 8th, with irregularities up to, in this case, 10 to the 9th per cubic centimeter. The electrons show the same behavior, but the electrons' hypothermal fluxes are typically about 4 to 10 times less than the hypothermal ion fluxes. And I think this shows one other feature that we see throughout all these storms, and is important for the exchange of energy between the magnetosphere and the plasmasphere, and that is, before the storm, the temperature stays fairly uniform. You see here it's about 2,000 below, something like 36, 30, 40 degrees invariant. But throughout the period of the storm, while there persists of something like an average temperature gradient of about 2.5 degrees per kilometer across the boundaries, the temperature increase into the plasmasphere is gradually increasing throughout the period of the storm until, and you can say, 2 days after the beginning of the main recovery, there still is tremendous enhancement, at least a factor of 2 in the electron and ion temperatures, down to very low latitudes in both the northern and southern hemispheres, down to maybe 30 to 40 degrees invariant on the night side. And I think this is an important source of heating on all of these storms. In the next slide, one might summarize the variation with, I should further say, during these periods, when we've examined all the SAR arc data, we always observe the SAR arcs occurring always poleward of the major plasmapause boundary. That is, there's also plenty of, this is where the temperature maxima occurring, and this is where all the SAR arcs occur at this boundary, and beginning at this boundary and poleward of this boundary, and not inside the plasmasphere. And I think this is very relevant to the kind of analyses that has been carried out by Cornwall and Thorne, Cornetti, etc. May I have the next slide? Oh no, I have to get it. Now, just for this storm, which is again representative of these 8 storms, just what we have done is to plot the location in L of the region of maximum density gradient at the equatorial edge of the plasmapause or trough throughout the period of the storm, and at the same time the position of the maximum gradient in the electron temperature throughout the period of the storm. And one can see that the temperature, and here is just before the storm started on October 29th, we can see they're slightly different at L equals 4.8, and the maximum temperature gradient at about 4.3. Then throughout the period of the storm, through the maximum disturbance, KP was 8 on this day, up through the recovery period, the location of the maximum temperature gradient and the density gradient are very close indeed. And the SAR arcs that we observe throughout this period are always occurring poleward at higher L shells, always poleward of this boundary. I think that it's of interest to see on OGO 3, we see, this is OGO 3, the electron density and electron temperatures which we measured with a similar probe as a function of L. And one sees, again, these are the storm of 25 June 66, and which Frank has reported on. I'll show some of his data. That is now this is Frank's data, that during the storm, you can see again at the plasmapause boundary, the temperature gradient goes very, very high. This is 15,000 degrees. The temperature does go up. And similarly, this shows at the location of the ring current, which Frank measured in our same electron density data, so that it's exactly at the location of the ring current that these maximum fluxes, soft particle fluxes, are occurring. Now, I think that the one thing one might note here, this is just some other Frank's data showing, comparing in the peak of the storm of July, our electron density data and Frank's ring current protons. And I think what's relevant here is that we all agree that it's all generally agreed that and as Cole has first pointed out, that the injection of ring current protons are the principal source of the major DST variations which are observed in these storms, and that these ring current protons are indeed the main source of the energy that produce red arcs. But that these, I think one point one should note is that while Cole has noted that these must primarily come from the conduction of heat by conduction from the magnetosphere to the ionosphere, the heated electrons then exciting the oxygen 6300 line, that Cornwell has noted in his source of the major mechanism by which this occurred was the excitation of ion cyclotron turbulence by the ring current. Now, actually, his conclusions say that this ought to occur within the plasmasphere, not outside. And I would say that this data in general shows that this is not true, that the location of the red arcs is always poleward of the plasmapause. And furthermore, that these hyperthermal particles show, we're not quite sure of where their origin is, actually, whether they're just the tail of the ring current particles or whether they're in fact particles being diffused upward. But I think that the thing is that one must note that there's enough energy in them, about 10 to the 8th per cubic centimeter, right in the location of the arc, to produce significant local heating in the ionosphere. And I guess if there is, just like to, the previous slide just shows that these results much more show the kind of result that Cole reported in 70 on where the superthermal particles ought to be relative to thermal at the boundary of the plasmapause. And what's wrong is his ordinate, I think. It's been objected to that you don't see this. Well, actually, if you change this not to density, but to energy density, what you'll find indeed that the very soft particles go out at the plasmapause, very low. Often we see almost none, less than 10 per cc. But actually, these particles, protons, which are typically in the ionosphere, 2,000 to 3,000 kilometers, have a density of about 10 per cc with a very high energy density. Okay, thank you.
I'm going to allow one remark. I think Andy's going to make the one I would have made, so I'll ask him.
The remark I'm going to make is that I'm surprised Rick Chappell didn't make. And that is that I think we have to be very careful with throwing around terms plasmapause. And for example, what your data shows that the red arc, occurs outside the ion trough. But that's not necessarily electron ion trough. That's not necessarily outside the plasmapause as seen in the equatorial plane. So let's keep these definitions very clear, because where you see that big drop in ion density or electron density at 2,000 or 3,000 kilometers, when quote mapped to the equatorial plane, maybe at a very different L value than where the plasmapause is at the equatorial plane. So what I'm saying that your observations are not necessarily contradictory with the Thorne, Cornwell, Coroniti suggestion that the red arc has to be inside the plasmapause.
But I'm not sure. I'm not totally sure I agree with you, but I know that Chappell and Carpenter have published results on the comparison of the location of the plasmapause and the trough on this day from OGO data and Whistler data. And we agree with the location of the L shallow, where that boundary is. When you map it down to the field lines, in particular this particular storm, we've tracked 3 storms where they have compared, and it is the L shallow on the night side.
I think there's another question of fact which doesn't depend on definition, and that is, are you saying, Rita, that there should be fluxes of superthermal particles in the region of the red arc?
Well, I'm saying that this is what we experimentally observe, that indeed, that in the region where the red arc occurs, where these peak electron temperatures occur, that we do indeed see particles with an average, these are after filtering the thermals, particles below 15 eV, we see these fluxes at very low densities, but fluxes of particles with typical energies between protons between about 40 to 150 eV.
I think the observation in the ionosphere, where the action is taking place, where the red arc is really being excited, is such that there probably are not any appreciable superthermal fluxes.
Well, these
It's
aren't very-
mostly an enhancement in T sub E.
Well, on the night side, these aren't so high. These are 1,500 to 3,000 kilometers, that data, that later data I was showing you. Well, they're measured. So this is not...
I want to make one comment that there were a lot of comments and a lot of discussions after Rita's paper, and I've got several requests for equal time and for a 5-minute discussion, but I know that would take a half an hour, and we aren't going to do that now. But there is a period later on in this meeting where the subject of red arcs really is specifically discussed, and I would suggest that we sort of prime ourselves to converge on that time and reaffirm that sort of thing. I also had a short request from Bob Ether to talk about the diffuse auroral zone, but I'm sure that's going to have time later on in the program too, and I'd rather not do that now.